All right, so you want to prove that this limit is equals to this result that we have here, and likewise the limit is x tends to 0 sin x over x equals to 1. How can you prove that this is true? All right, and how close do we need to get to 0, for example, for this limit to be true? All right, so what we're trying to say is we're trying to make the definition of a limit precise. All right, so we don't want to give vague statements such as x gets closer and closer to 2. We need to be exact at our definition. For now, I'm just going to skip all of this and go to the definition. You can look at all of those. All right. Now, this is where you need to pay attention. So let f be a function defined on some open interval that contains the number a, except possibly at a itself. All right. There you see the limit of f of x as x approaches a is L. So this is just what limit as of f of x as x approaches a equals to L looks like. Now, for precise definition, this is true if for every number exodum greater than 0, so we call this exodum, there is a number delta greater than 0 such that the distance, all right, the distance between x and a, where is this coming from? Remember, it says x approaches a, so we look at the distance between x and a. If that distance lies between 0 and delta, then we see that the distance between the function and that output that we get L, so the distance between those two is less than exodum. All right. Take note, absolute value just means distance. All right. So how would you use this definition to solve a problem? That's all I need you to know when it comes to precise definition. How are you going to use it? I'll go to a very straightforward example. Look at this example. Prove that this limit is equal to 7. Now, if you notice it, I didn't mention that use precise definition of a limit. But to do you a favor, if I ask you precise definition in the test, I'm going to tell you that use a precise definition of a limit to prove that this limit, for example, is equal to 7. All right, I will tell you just so that people don't do some funny stuff. How does it work? Preliminary analysis of the problem. So I need you to show me all of this step by step. All right. So you let exodum to be a given positive number. So you can just say let exodum greater than 0. You say let exodum greater than 0. We want to find a number delta such that if the distance, take note your a now is 3. So your a in this case is 3. The distance between x and 3 lies between 0 and delta. Then your function, which is 4x minus 5, the distance between the function and 7 is less than exodum. So you need to be able to state all of this. So let exodum greater than 0. We want to find a delta greater than 0 such that if that distance between x and a lies between 0 and delta, then the distance between the function and the function output is less than exodum. You should state this first step. Then your next step is just look at this piece on its own. So the distance between the function and that output is 7. Try to simplify that. Simplify it to a point where you see a relationship between this term here, which I circle, and what I'm underlining here, x minus 3, all right? Let's see how it works. If you simplify this, it just becomes 4x minus 12. Remember, minus 5 minus 7 is minus 12. And again, we don't see the x minus 3. We need to simplify a little further. If you factor out the 4, notice it, you start seeing x minus 3 appearing somewhere. And we typically want x minus 3. So you take out the 4 from the absolute value. So you factor out this 4, you left with absolute value, x minus 3. Now, this is so important because we should be able to compare what we've simplified to this first statement here, all right? You see x minus 3 absolute value here, and it also applies here, therefore we can do a direct comparison and see what the relationship is going to be between delta and exodum, all right? So once you've simplified that, if you've seen this thing appearing, what is your next step? The next step, you go back again and you state Therefore, we want a delta such that if the distance between x and 3 lies between 0 and delta, then remember this is what you simplified, all right? 4 into absolute value x minus 3 is less than x. That is, we can simplify even further. If the distance between x minus 3 lies between 0 and delta, then they are just divide both sides by 4. So the absolute value, x minus 3 is just less than x over 4. Now look at this statement here. This statement and this one here. All right. You already see the relationship between delta and x. This suggests that we can choose, this is so important, we can choose our delta to be x over 4. All right, you can see, because here we have the distance between x and 3 is less than delta, the distance between x and 3 is less than x over 4. Therefore, it suffices that we can choose delta to be x over 4. All right. Again, you go back and state the whole term. So, given x greater than 0, we choose delta equals x over 4. All right, what does the statement now become? If the distance between x and 3 lies between 0 and delta, then this whole simplification, you've done it already, so just rewrite it. This whole thing becomes 4x minus 12. If you factor out 4, take note at this step, because you say that the distance between x and 3 is less than delta, therefore if you say 4 times absolute value x minus 3, if you multiply all three here by 4, take note you just end up getting something less than 4 times delta. All right. So 4 times this will typically be 4 times delta. I hope that makes sense. All right. If this is less than delta, if I multiply by 4 on both sides, I'll get that 4 times this absolute value is less than 4 times delta. Why do I do that? Because we choose our delta to be x over 4. Where I see delta, just put x over 4. And take note the 4 cancel out and I'm left with x. So whenever you simplify your precise definition, you just end up getting x. All right. This is the step where you prove. So this is step 2. Step 1, you let x greater than 0. You find the delta greater than 0. You write the whole definition. You simplify. You find the relationship. You choose a value for delta. So you find the relationship between delta and x, and you tell me what you choose your delta to be. Then step 2 is to prove that what you've chosen actually works. All right, you need to prove that this value that you choose here, delta equals x over 4, works. All right, how do you prove that it works? You just write this whole statement again, but now you need to use the fact that if this distance is less than delta, if you multiply by 4, obviously it's less than 4 times delta. All right, and in place of delta, you just put in x over 4. You see, you get x. You're done. All right. Then, hence, you can say as a conclusion, if the distance lies between 0 and delta, then this whole thing is less than x, and therefore you can conclude by the definition of a limit that this limit is equal to 7. That's all you have to do. All right. Remember, if I tell you that prove that this limit is equal to 7, it means it is actually equal to 7. I'm not asking if it's equal to 7. It means if you use your precise definition, you choose your data wisely, it is definitely going to work. All right. That's the one example. This is the most straightforward form that we usually ask in the test, the linear form. I'll try to not ask you quadratic and so on. So for the linear form, this is what you need to know. There's something in addition that you need to know. It's called one-sided limit. So let's see. This is definition of left-hand limit. Now you have a limit as x approaches a from the left of f of x equals to L. See how the definition changes? You say if for every number x greater than 0, there is a number delta greater than 0 such that, you see the first part here changes. You have x lies between a and a minus delta. All right, so this is what changes. If you have the limit as x approaches a from the left, you see that on the left of a, you'll be subtracting some delta value. All right, let's see if we can. Okay, yeah, they're just telling us what the definition looks like to the right. Obviously, if you subtracted some data to the left, when it's a to the right, you're going to be adding some data value to a. All right. Let's look at an example. So we've seen 3 definitions that you must know. All right. When x approaches a, when x approaches a from the left, and when x approaches a from the right. All right. Let's see how we can do this. They say use definition 4 to prove this. This is as x approaches 0 from the right, all right? So we already know that we're going to have x uh, lies between a and a plus some delta, all right? So let's see how it works. So write the definition. Let exodum be a given positive number. So instead of saying being some given, just say let exodum greater than 0. All right, save time. Instead of writing too much English, just say let exodum greater than 0. We want to find a delta greater than 0 such that x lies between 0 and delta. Now remember, if you go to that definition, x lies between a and a plus delta, but a is 0. So it's 0, and on this side you have 0 plus delta, which is just delta. All right. And then you have the function, which is root of x minus 0, or the distance between the function and the output, which was 0, is less than x at. This one seems very straightforward and easy. That is, what does this mean? It means if x lies between 0 and delta, then remember root of x minus 0 is just root of x. So root of x is less than x at. If you square both sides, you get that if x lies between 0 and delta, therefore x is going to be less than x at squared. All right. Now you can choose your delta already. Look at it closely. This is a relationship. X is less than delta, x is less than x at squared. Therefore, we can choose delta to be x at squared. There we go. Straightforward and easy. Now, when you choose, I'm sure you can already guess what the next step is. You need to show that what you choose works, all right? How do you show that it works? You go back, you say given. Remember in the beginning, you said let x at greater than 0. When you prove it, you say given that x at is greater than 0, we have chosen our delta to be x at squared. We say if x lies between 0 and delta, then root x is typically less than root of delta. If you remember well, we had x less than delta. So if you look at this relationship here, x is less than delta. Therefore, if the function is root of x, therefore we're going to say it's also less than root of delta. All right? Why do I need root of delta? Because if I substitute what the delta is, which is just x at squared, I have square root of x at squared is equals to x at. You see, if you can't simplify your output to get x at, I can guarantee you're already making a mistake. All right, you're wrong. It's as easy as that. You should get x at. All right. And take note, if you have x at squared, ask yourself in advance, what do I need to do to x at squared to get x at? I need to find root. That tells you that once you hit the step here, you should be looking for root of delta. All right. So the distance between root of x and 0 will be less than x at. And according to definition 4, you can just say therefore this limit, according to the definition of the limit, this limit here is equal to 0. All right. So first thing, simplify your definition and then choose a value for delta, and then step 2, show that it actually works, and then just write a conclusion that by the definition of a limit, this limit is just equals to 0. All right, so it's easy as that. Now we've seen the limit as x approaches a number a, the limit as x approaches a number a from the right, and obviously from the left. From the left, instead of having x between 0 and delta, you're going to have x between 0. On this side, you're going to have 0 minus delta, all right? So that is the only difference that you're going to have. Now, let's look at another. So for now, you have two limits. Obviously, you should be able to prove that this limit is equal to L plus M, all right? If this limit is equal to L and this limit is equal to M, therefore the limit of f of x plus g of x is just L plus M. So this is more or less you doing a combination of precise definition of a limit. But trust me, I'm not going to ask you that, all right? Because you guys struggle already with the linear function. Infinite limits. Also, this is very, very important. You must know infinite limits. All right, this is the fourth one that you need to know. All right, infinite limits. How does it work? See how it works? Now your limit as x tends to a goes to infinity. You see here? Infinity, not the number, it just goes to infinity. Once you see that, if I say show that this limit equals to infinity, using the precise definition, you know you're looking at this definition. What changes? Look at it carefully. This first piece here looks the same as we did with our first example, the linear function. the distance between x and a lies between 0 and delta. Then look at the second piece now. Your function needs to be greater than m. Take note, m is just for some positive number, all right? You say for every positive number m, there is a positive number delta. Like I said, you can replace this whole statement by just saying that let m be greater than 0. We're looking for a delta greater than 0 such that if this is true, therefore this is true. Done. All right. Or if you care, you can write positive number. Like I said, you can just use greater than 0 in the place of saying positive number. This is just how we visualize it graphically. Okay, let's look at this example, guys. Pay attention to this example. The limit as x tends to 0, 1 over x equals to infinity. All right. Let m be greater than 0. Another person say let m be that given positive number. Fine. We want to find a delta greater than 0 such that, look at this carefully, the distance between x and 0. Remember, x minus 0 is just x. That's why you just see absolute value x. Right. The distance between x and 0, if it lies between 0 and delta, then your function, which is this whole thing here, is greater than m. All right. How do we simplify this? You say, but 1 over x squared greater than m, what does that mean? It means that x squared is less than 1 over m. All right. Remember, if you take the reciprocal of an inequality, the inequality sign changes. So if you say 1 over x squared, which you just get x squared, your inequality sign changes to less than. All right. Then you have 1 over m this side. Now, what does this statement again mean? How do I simplify? Remember, I said you need to simplify this statement so that you see a relationship that looks like this. Absolute value less than some number. All right. How I get to that simplification? Remember, x squared is the same as, if I simplify that, I can take square root on both sides. So if I take square root of x squared and I take square root on the right hand side, I end up with absolute value of x is less than 1 over root of m. Remember, absolute value of x is the same as the square root of x squared. So that is a definition you need to remember. Absolute value of any number a is exactly the same as the square root of that number squared. All right. So once I apply square root on both sides, take note this left hand side simply becomes the absolute value of x. All right. And looking at this, we're good to go because this looks like this relationship that we're looking for. I have absolute value less than something. Here I have absolute value less than delta. Therefore, I can choose a value for delta. And what do you choose? Obviously, everyone can see we choose delta to be 1 over root of m. All right. So this delta here looks like this one here. All right, 1 over root of m. And like I said, you just keep stating the whole thing again. If the distance between x and 0 lies between 0 and delta, remember that your delta now is equals to 1 over root of m. Then you can say that 1 over x squared is greater than m. All right. And this shows that as 1 over x squared approaches, so 1 over x squared will tend to infinity as x approaches 0. All right. Or you can go ahead and say by the definition of a limit, this whole thing is equals to infinity. All right. I know most of you ask a question, you don't understand this last piece here. All right. What really happened? If you choose your delta to be 1 over root of m, all right. So if delta is 1 over root of m, what is 1 over x squared? Now I want you to think clearly. 1 over x squared will be, so 1 over x squared will be 1 over m. All right. And remember, if you say 1 over x squared, you simply take in the reciprocal. Again, it changes back this less than to greater than sign. All right. And you just end up with this whole function greater than m. Remember, that was the definition, the precise definition for the limit that goes to infinity. You want your function to be greater than m. All right. So the trick here is just to be able to find that relationship that I tell you, to choose the correct value for delta, and then from there, you're almost done, right? Or you're more or less done. And obviously, take note, you can go to minus infinity, all right? Limit can also go to minus infinity. What is the difference? The difference is that instead of saying that for every positive number, this time we need for every negative number. Also tend to mix these things around. This time when you go to negative infinity, you want for every negative number n, there is a positive number delta, so that if the distance between x and a lies between 0 and delta, therefore your function is less than, not greater than, this time is less than n. All right. So for positive infinity, you want a positive number m, and your function must be greater than m. When the limit goes to minus infinity, you want a negative number n, and your function has to be less than n. All right, and you just follow the same procedure. Any question from your side? I'm just going to stop recording.